Okay, so I promised you a derivation of arc length, and so I'm going to go over that now. It's kind of one of my favorites. There's a lot of interesting things about it, and I think it really shows you the power of sums. It's not as obvious, say, as a volume. Anyway, this is the formula that we have. And so what I want to address is y. And by arc length, remember what I mean between 2 points on the graph. So, AF of A, BF of B. I want to find that length. And this integral does that. And so in the derivation, there's a few key ideas. So here's a graph, and I've exaggerated a little bit, but I've taken sort of I've drawn the rectangles, but I'm not going to use them to find area, but I'm just indicating right here where my delta xk is, so between xk minus 1 and xk. And then what I'm doing is I'm connecting 2 points, these 2 points on the graph with that straight line. It's a hypotenuse of a triangle. And that triangle is going to be, the base is going to be delta x, clearly, and the height, which might be a little bit harder to see, is going to be delta y, because it's the difference in these two y coordinates. So delta x down here, delta y here. And it's typical to call a small piece of the graph ds, using differential notation. So what I'm saying is that this small piece of the graph is pretty close to LK. So that's what I'm saying down here. And it turns out that LK is a hypotenuse of this triangle, so that means we can actually measure it, delta x squared plus delta y squared. Okay. And I'm going to come back to all these ideas during the derivation. I just want to get them out of the way right now. And the third key idea is that you can factor anything out of anything. For example, a plus b, I can factor a c out of that. A over c, b over c. Or I could do this, a over b, I can factor an a out of the a, clearly. But if I factor it out of the b, I have to divide by a to compensate. And again, why is that? Well, if you want to check it, it's pretty clear you get a that cancels there, plus b. Okay, 3 key ideas. This triangle here, the hypotenuse is close to the graph, and we can factor anything out of anything. Okay, so now we'll start with the derivation. So I've started it over here. What I've done is I've taken, as I usually do with a integral, I divide it into, start with a and b. A is equal to x0, b is equal to xn, in this case 3. And then I divide it into rectangles. But here I'm going to do something different. I'm going to form those 3 triangles right there. They're kind of like slope triangles. Delta x, delta y over here, delta x here, delta y2 over there, and so forth. And then I've made the hypotenuses here. And you see these lines, L1 plus L2 plus L3, is going to be pretty close to the arc length. That's what I'm trying to say here. Okay. Again, take the graph, divide it into n sections, connect the points in each section. You form a triangle, the base of the triangle, delta x, the height of the triangle, delta y. And if you add up all these hypotenuses, you get close to the arc length. So we'll follow that. Okay, so I'm going to start here. This right here is equal to k equals 1 to n lk. Okay. Now I look at lk, and it's going to be equal to, sorry, I should have probably said it this way. Lk squared is equal to delta x squared plus delta y squared. So if I want to solve for lk, I need to take a square root. And that's how I get this. Okay, so now I can substitute that in for here. Sorry, this will take a second to write. Okay, well, okay, now I want to turn this into an integral, but I need a delta x. And this is where I'm going to use the trick. What I'm going to do is I'm going to say, well, delta x k squared plus delta y k squared, that's going to equal 1. I'm going to factor the delta x squared out of that, delta yk squared. Okay. And then in order to factor this out of this, I need to divide this by delta xk squared. So in other words, I factor delta xk out of this, turn that into a 1. I need to divide that here. So now I can go over here, and I can rewrite this as square root 1 plus delta y squared over delta x squared times delta x squared inside the square root. So I'll break that into 2 square roots. Okay. Okay. And I can easily rewrite that. Take the square root. Okay, so now I have my delta x. Sorry, there should be k's on all these. I'm just lazy. Because this is just a typical rectangle. Okay, now I want to kind of look here that this is close to f prime of x. We've said that before. So what I have here is, if I bring this down, I have that my arc length, s, is close to this. Okay. Now, how do I make it equal? Well, I take a limit of that. I let the delta x's go to 0, and when I let the delta x goes to, as delta x goes to 0, what's going to happen is that delta y over delta x, it's a y on top, is going to go to f of x. So I take my limit as the biggest delta x goes to 0. I get a 1 here. That becomes f prime of x squared. And you know from past experience that this becomes dx. I'm sorry, stupid me. That's still delta xk. Okay. So basically what I'm saying, I start off with s, approximated by the sum of the hypotenuse. I go through the algebra here. So you can go over this again if you want. I get s as approximately this. I take the limit, and then what I get is this sum, and this sum over here, well, let's turn it into an integral. I get integral 1 plus f prime of x squared. That becomes a dx, and I get ab, and there's my arc length integral. So basically all it is, it's Pythagorean theorem, some fancy factoring, and taking the limit. And you get this interesting formula. Okay, I'm going to do an example in a different video, but thanks for your time for this video.